Howdy, I'm Professor Parks, PhD, and I make content on astronomy. Let me start that again without the YouTube in the background. Howdy, I'm Professor Parks, PhD, and I make content on astronomy, science, skepticism, and mental health. Welcome. And today I'm going to be talking about my experience with the total solar eclipse that happened on April 8th. So welcome. So yeah, it excuse me, it's going to be a little bit chaotic today because one, I woke up late, and two, for some reason, I continue to think that my introductory astronomy class is at 1:30 when in fact it's actually at noon. So that prompted me to actually get online faster than I had anticipated. Anyway, so yeah, howdy, Billywood, Trucker, Clive, always good to see you. And yeah, so let's get started, I suppose. First thing I want to do is I want to talk about negative parallax. Now, this is specifically for space audits, Alan. The genesis of this is I was watching. So, Space Audits has a flat Earth debate on X Spaces, which I told him I do not support Elon Musk in any way, and so I refuse to use X or anything that Elon has any kind of influence with. I don't know how I'm going to rectify SpaceX, but thankfully SpaceX is not something that I have to buy or work with. So that being said, I was watching one of his debates on flat Earth or what have you, and he had a guest speaker really on whose name I don't know and couldn't be bothered to ask. And he went on the usual sort of, I would say tirade, but that's impolite. Litany, better word. Litany of problems with the heliocentric model, and one of them was negative parallax. And yes, Dr. Wells, I certainly will. That is a life goal of mine. And he brought up negative parallax, and I, mentioned in the chat of Space Audit's stream, which is what I was watching this on, that I have explained negative parallax multiple times. And howdy, Professor Phil Bell. I've explained negative parallax multiple times, and frankly, I'm getting kind of tired of it being brought up over and over again. But I also recognize that I am but a small voice in this entire in this community, so I will have to address this directly again. I'm going to snip out this portion and post it as its own video. So hopefully, if I could just refer to that, be like, "Hey, watch this." I would like to have visuals, but I'm not prepared for that. So I might actually redo this. Anyway, negative parallaxes. So if you look into the technique of trigonometric parallax, particularly in the age before Gaia, you might notice that certain stars, a fair amount of stars, to be honest with you, have what appear to be negative parallaxes. And this ultimately has to do with precision. And the speaker on this X channel or X program made a snarky comment that he would not accept that it's measurement error or what have you. Well, whether you accept it or not, That is the actual truth of the matter. Now, trigonometric parallax is often displayed or often shown in a very simplistic way, in that the idea here is because of the Earth's motion around the sun, we have different line of sights to nearby stars with respect to a background. So if the background's up here, my nearby star is here, and I'm down here, then my line of sight will put the star over to my left with respect to that, to me, to those background stars. If I move to the other side of the orbit of the Earth, then that's my line of sight will hit that star and then place that star to the right of the background field. And if you follow that around, what you find is that this, depending on the declination of the star, it will either go this way, it will make a circuit that is left-right, that is a straight line, that is if it is in line with, excuse me, not declination, ecliptic longitude, or ecliptic latitude. If you're along the ecliptic, it's going to be a straight line. If you're farther away, say, and then as you get to the pole, you're going to have a perfect circle, or rather, actually, you'll have a path that is identical to the orbit of the Earth, which is actually slightly elliptical. And then everything else falls in between. It's very similar to the aberration that we see with starlight. However, aberration is, because it is dependent on our orbital velocity, is basically fixed for all stars. You're not going to see a difference in aberration from one star to the next. With trigonometric parallax, you will, because there is strictly speaking a distance measure, or a function of distance. Yeah, I'm definitely going to redo this because this is a little bit more chaotic. Anyway, so it's usually depicted as you take an observation in June, you take an observation in December, and bing, bang, boom, you get the distance. Well, first of all, there's a certain problem with this. You can't actually do that, at least not for a good chunk of stars, because they're not going to be available to you, because, the sun's kind of in the way. Stars that are available in June, generally speaking, are not available in December. How trigonometric parallax is actually done in practice, and I think I can speak fairly authoritatively on this, because while I have never done trigonometric parallax myself, I got my degree in a department that there's a research group that specializes in ground-based trigonometric parallax. It's called RECONS. You can look it up. It's RECONS, all capitals. They are based at Georgia State University, and they have mapped out all stars, the distances of all stars within at least 10 parsecs, which is roughly 30 light years, and are working on a 25 parsec volume limited sample, meaning they're going to find every single star within 25 parsecs and provide an accurate measure of its distance. And then I don't know what the status of that is. At this point, they've probably completed it. And I would imagine they're going to try to do a volume sample of 50 parsecs after that. So the way they do trigonometric parallax is they don't observe twice. They observe constantly for as long as the target is in the sky at an appreciable altitude, because they don't want to look at these stars at low air mass or low on the horizon, because of atmospheric refraction, its position is going to move around far too much for this. Trigonometric parallax is an exceedingly laborious process. It requires a exceedingly stable platform. Any kind of vibrations within the telescope any kind of changes to the optics are going to introduce errors that are going to really just flood out your signal. They're going to make precision measurements impossible. So it's not like if I tried to do it here at George Mason, this telescope is not stable enough to do it, mainly because for some reason, the way they designed it, we actually see vibrations due to probably the fucking HVAC system. The HVAC system, we believe, is vibrating the building enough that we see an error we see the stars shift noticeably in deck. Like the thing is literally bouncing. So it requires an extremely stable platform. These telescopes are dedicated to doing trigonometric parallax measurements. The idea is you take your target star. This is the star that you want to know the distance to, and it's against a background field of stars. What you do then is you take that star and you compare its distance, angular distance, to a number of different stars in the field. Ideally, those stars we already have distances to them, so you know their actual positions extremely well. And you can take into account that those stars are also going to have parallaxes in and upon itself. And ideally, you want that parallax to be so small that that star is basically stable. But from my understanding, there are ways of getting around that issue if you have parallax, if you see parallaxes in your background sky. So you take that star and you measure it to a number of different reference stars. Because the idea here is, again, you will have parallax in those background stars, but those parallactic measurements are going to vary significantly, or significantly enough around those stars that from a statistical average, you can mitigate that on top of any other methods that you want to, or that you can employ. So it's not just a star. You're not comparing this to a star. You're comparing this to lots of stars. And you take images over a long period of time. Like I said, as long as you can see this object, you do it. And they've done it and they don't do it simply over one orbit. They do it over multiple orbits in order to really damp down that error, to be able to actually see the signal, to pull out the signal from any sort of random noise or systematic noise in the instrument, or due to atmospheric refraction, or a number of other things that I can't think of off the top of my head. But they do over multiple orbits. Again, this is a laborious process. This is not something that is just, fuck it, we're going to take couple of trigonometric parallaxes and call it a day. The issue becomes that the distance determined by trigonometric parallax is, let me back up. The thing is that the distance found via this method is an inverse function of that parallactic angle. That parallactic angle effectively is the shift that the star appears to have over time with respect to those background stars. Now, what we do is we find that star's relative position to the rest of the stars on each night from each of those data, or from each of those images collected on those nights. And that gives a particular position. You then put all of those positions together. You then basically take an average of those positions as found from all of the observations over multiple orbits. And you plot that as a function of time, effectively. You are trying to map out that ellipse that you are going to see based on this phenomenon. As I said, the technique is the angle decreases as a function of distance. So if you're looking at something that is far enough away, then the parallactic angle is going to be smaller than the systematic errors in your instrument. Again, if you don't want to accept this, then I don't know what to tell you. In reality, all measuring instruments have error. And as a practitioner of science, as an experimenter or an observationalist, you need to know what that error is exceedingly well. You need to be able to define what the errors are in your measurements in order to essentially back up your claims later on. If you provide a distance that the errors are so large that basically the errors are of your instrument is the error in your parallactic angle is on par with the parallactic angle itself, then that can't be trusted. And we know this as a community. Well, getting to negative parallaxes. When you get to that, when you make these observations, and you look at the position of the star over several orbits, again, because of the error involved and because of the size of this parallactic angle, the output can in fact be negative. We as a community know what this is. We know where this comes from. And we, generally speaking, don't publish these results. We basically say that we don't know the distance to this thing. We can't trust the distance to this thing. So, because we recognize that a negative parallax is unphysical, that it's not possible to, it just doesn't correspond to physical reality. And because we recognize that it doesn't correspond to physical reality, we discard those measurements. But I can assure you that is the reason for negative parallaxes, is that the star is at the limits of the capability of the telescope that is attempting to determine the distance. If you had another telescope which has better precision, they're able somehow to damp down those systematic errors, then they will get a parallactic angle to that star that is non-negative, that is in fact positive, and hopefully with errors that are small enough that you will have confidence in that measurement. So effectively, that is what negative parallaxes are, and that is where they arise from, and that is our reaction as an astronomical community. It does not make any sense to point to these negative parallaxes as examples that the technique as a whole is fraudulent or is not a reliable technique in order to determine distances. That is simply a false assertion. Because again, if you have a precision that is good enough, if the error in your parallactic measurements, the angle, is small in comparison to the parallactic angle itself, then you can trust that observation. And again, I cannot stress this enough. This is a laborious process with a multitude of data. This is not something that you take 1, 2, 3 points of data and then run with it. You have hundreds of points of data from which to extract this information. Because again, we know how difficult it is to do this, especially from the ground, because of atmospheric refraction. The geometry, the underlying principle is sound. So if you want to reject trigonometric parallax as a method, to determine the distance to a star, then you really need to explain why the basis of the technique is flawed. What is it about this technique that cannot give or provide an accurate distance measurement. What is it that we are missing as astronomers? What is it about this technique that is flawed? So, with that, that is my explanation of trigonometric parallax. Maybe in the future, I will cut this and try to edit it so that it is not so rambling. And maybe in the future, I will attempt to add some visuals to it. Maybe as I'm editing it, I will put some visuals to it, and I will put this out there as a solo video, letting people know what this technique is about. And my hair, I'm just having a bad hair day. I hate this intermediate stage of growing out my hair. I'm weird. Anyway, so squirrel. So yeah, that's it. But you know, trigonometric parallax is not what I came here to talk about. What I came here to talk about is the eclipse. So if you'll indulge me, I need to pull some stuff up. All right, if you are a member, and this is my e-begging plug, I have both Patreon and channel memberships. If you would like to have access to videos and to resources that certain videos and certain resources, please consider becoming a Patreon. And I believe, let me see if I can put this up. Nope, that's not what I wanted. That's still not what I wanted. Banners. There it is. There you go. There's my Patreon. Or consider becoming a channel member. For instance, I took a video, 90-minute video of the eclipse using my new snazzy C-Star, which I was able to purchase due to the largesse of my Patreons. Thank you so much for giving this to me, or helping me be able to purchase this thing. It is a godsend, and I haven't stopped using it since I was able to start using it, primarily because of this solar project that I'm doing. But I digress. All right, so before I show things, actually, let me set the scene. Let me tell you what I was doing. Before I do that, let me ask this. Oh, howdy, Versor83. Are there any good sequences of very many photos that show the trigonometric parallax of a close star over a year? I haven't been able to find them. Neither have I. And I don't know why. It might be that my Google foo is not appropriate. At this point, I think I'm just going to have to email a couple of folks that I know back from who were in or still in the recons, and see if I can get my grubby hands on any kind of data that they've used. Basically, the data that is now public domain. And because I still can't find my friggin' heater for my kettle, I am now getting kind of addicted to these Monster Energy drinks. I'm going to need a new kettle. For the love of God, I will not drink these on the regular. But I got to have that caffeine. So yeah, I've looked fairly extensively as to try to find even just a real world example of showing the star moving from one in the field. I can't even seem to find that. Which I could go off on a tangent, which I won't, about the transparency within the astronomical community and how they share data, but that is not what I'm here to talk about. What I am here to talk about, again, is the eclipse. So the eclipse happened on April 8th. Long story short, the eclipse, depending on where you are in the country, will either be a partial eclipse or a total solar eclipse. I have never seen a total solar eclipse prior to the 8th. Yeah, for me too. And so I was determined to see this damn thing this year. because I have heard many, many stories about how almost life-changing it is to witness this event. It is an extremely surreal event where the sky darkens considerably. Effectively, I can now tell you from experience that it becomes it's similar to late twilight, late dusk, um, or early dusk. And I'll show you what I mean in a moment. There are a number of things. And during totality, you can look with your eyes unaided or unfiltered only during totality. Do not look at the sun without proper filters. But when you look at the sun in totality without a filter, you can literally see there is a hole in the sun. There is a black disk covering part of the sun. And so, yeah, surreal. Ultimately, a very surreal experience. And so I was determined to see this thing. And because of events, I also got put in charge of our entire effort here at George Mason, which included helping a team, one of our astronomers here in the department and his suite of grad students who are going to Dallas because we are able to predict eclipses pretty well. This group of helio astronomers who are dedicated to studying the sun, whom, by the way, are all just a little bit off as a group. Gotta say, solar astronomers, I don't know what's going on with them. Probably because they're dedicating their lives to one star. Anyway, so they have a conference every year, and lo and behold, they decided to have their conference in Dallas, which is in the path of totality. It's funny how that works. So I needed to provide them with the equipment and the training in order for them to take images of the eclipse. In addition to that, I was needed to provide the equipment and training for a group that was going to be the home team here in Fairfax. While it is only a partial eclipse, 89% coverage of the sun, it is a big deal, and so I need to provide them with the proper with the solar with the eclipse glasses, the telescopes, the filters, all that sort of thing. And then on top of that, we had what is called the P&P team, or Plavchan and Parks team, where we took a number of students, around 35 students, to Indianapolis, and we experienced the eclipse in the racing capital of the world, or at least that's what they claim, the Indianapolis 500 Speedway. And so we brought two telescopes. One was my Sea Star, which is laying over there, which I will be taking out with me to my class because it is sunny outside. And so I need to take yet another measurement of the sun. But also, we took our LUNT, which is, in this particular LUNT, is a solar telescope that is specifically filtered to look at H alpha. This is a telescope that is designed to look at one object and one object only. If you try to use this telescope to look at anything else, including the moon, you wouldn't see shit. It is so heavily filtered that the only object bright enough for this telescope to view is the sun, and it specifically is tailored for H alpha, which is a line in the hydrogen spectrum. Specifically, it is the I should know this, 3 to 2. Yes. I really should know this. The wavelength of the line is 656 nanometers. I believe it is the 3 to 2 transition. I will have to get back to you on that. That's embarrassing. I do believe it's the Balmer series. You're transitioning to the second orbital, and now I'm getting into the weeds. Anyway, this is a very prominent line, which is specific to hydrogen. And the reason why that's important is that a lot of the magnetic activity on the surface of the sun is best seen in H alpha, where you are looking specifically to what is happening to the hydrogen gas. So we have two images or two different experiences of the recorded experiences of the eclipse, one in white light, which is the C star, CC. CC had a filter on her that blocked out all light from all across all wavelengths. It's what we call broadband. Now, the image that you'll see, the sun appears to be orangey. The reason for that is that while it is blocking out light from all wavelengths in the visible spectrum, it does not do so equitably. It is blocking out more blue light than it is red, and so that is the reason why it appears orangey. In the H alpha scope, it is definitively red, and that is because you can look this up, you can Google it. The H alpha line is red. It is at 656 nanometers, which is clearly in the, or is solidly in the red part of the visible range. And so we have that. One of the goals I have probably over the summer, given my workload, is to actually have a side-by-side comparison of the eclipse with that is appropriately synced in time to show you what the eclipse looks like as it goes, both in white light and in H alpha. Now I am reminded that I forgot about the whole, or maybe I didn't, about the whole membership thing. So I put up the video of the entirety of the first half of the eclipse, the totality, and a little bit afterward, because I know that the back end of the eclipse basically just looks like the first end of the eclipse in reverse. So I'm like, I kind of want to go home because it was kind of a long trip. So I stopped it there, and it is a video on YouTube that is strictly for members. Eventually, I have clipped, and I'm actually going to show it to you. I have clipped where it's just totality. And should I show that first? I should show that first. All right. So, what do I got here? And I soon will be posting this to social media. Nope. This is some work. I think this is some work. Dun, dun, dun. Where are you? There it is. Let's move you over here. Go back to you all. And let us present share screen. There we go. Yeah, let's put me in the corner so this is more spectacular. Should I use unfiltered binoculars to look at the sun? No, you should not. That is bad, okay? Bad. Also, do not look at the sun with binoculars and eclipse glasses, because I kind of did that, and it burned a hole in my solar eclipse glasses pretty much instantaneously. So I know this may have been a joke, but just to cover the bases, no, do not look at the sun without it being filtered using any method except projection. Yes. It is not, and I say this, and I'm emphasizing this because it became a kind of a popular talking point that right after the eclipse, the amount of searches for eye pain in Google went up dramatically, spiked during the eclipse, and for a couple of days afterward was still trending. So yes, do not look at it. Nimrod, you want to melt your eyeballs? Well, okay, that seems weird, but all right. So let's talk about this, and this is in real time. So this is just prior to the totality, and yes, it is in fact moving. So it is actually progressing. Again, this is in real time. This video is 10 minutes long, and so I probably will advance it in a second. But what I want to really talk about is, at this point, it was pretty dark. It was, you couldn't see any stars or anything of that nature, but it was getting kind of eerie in that we were sitting there and it was getting a bit chillier. It was getting darker. Kind of think about what happens when you're in the middle of a sunny day and then suddenly, clouds roll in and the sun gets blocked by those clouds. That's kind of the impression. I kept thinking to myself, are there clouds? Like, this really feels like there are clouds coming in. I knew what was happening, but my brain still was like, are there clouds coming in? Because at the time of the observation, there was a lot of cirrus, high level cirrus in the atmosphere, and it almost seemed like God was preventing everyone from seeing this because the path of totality happens to be essentially the same shape as weather fronts as they pass across the continental United States. And at that time, there was a front coming through. So a lot of people got clouded out. But thankfully, that front, there were a lot of gaps in the sense that while they weren't exactly crystal clear, except ironically in Vermont and Maine, the clouds were thin enough that it really didn't affect things. So, yeah, I was looking through high Cirrus, and so when this was happening, I was like, "Is cloud cover coming in?" But no, it was actually the eclipse. So, light cloud cover does not filter. Is not a sufficient filter unless you're looking again in totality. And yeah, there you go. We're seeing the eclipse, the moon. I will talk about that in a moment. Actually, I do not. This is a fairly small field of view. The field of view of this, I calculated it, but effectively it is half a degree or a little bit over half a degree left right and about a degree up down. So rectangular. It is a TikTok TikTok appropriate formatting for this, specifically because it is meant to be it's controlled by an app on your phone, and then bye bye. So at this point, I take off the solar filter because, as you can see, it is filtered enough that or it's dark enough that the solar filter is too much, and then boom, you've got that. And so let's talk about this for a second. The white diffused area that you're looking at is what's called the solar corona. The solar corona is still something of a mystery. And it is often noted by astronomers that given the wealth of information that we have about the universe, it's a little ironic that we still have very open questions about some of the most fundamental layers of the sun, the closest star to us. The corona is a rarefied gas that has an average temperature of 1,000,000 Kelvin. Now, you may have heard of the Parker probe. The Parker probe is the first satellite artificial satellite to pass through the corona in order to collect data. Because, as I said, what the corona is and how it attains such temperatures is still something of a mystery. And you might think to yourself, how can that possibly be? It should melt. Well, the reason for that is because, and I should say that I eventually, at some points, I adjust the gain so that I can try to bring out that corona. So some of what you're going to see is not real. It is simply manipulation of me, or it's my manipulation of the game, like that. That is me changing the game such that I can trying to bring out the corona, or the corona. The corona, again, like I said, is so rarefied that the particles which are responsible for the protons, the electrons, that are responsible for the transfer of energy are so few that the amount of energy being transferred is very small, or is small in comparison. The million Kelvin corresponds to the average speed of these particles. These particles are moving very, very rapidly because of the, as described by that temperature. But again, there are so few of these particles smacking into the probe that it is not experiencing what we would experience as a million Kelvin here on the Earth's surface with our atmosphere and our atmospheric density and pressure. The mystery is, why is it that hot? As we look at the atmosphere, colloquially known as the atmosphere of the sun, the chromosphere, and the corona, the temperature actually increases with distance. The average speed of the particles within those regions increases with distance. We don't know exactly why. We have some guesses as to why. The consensus at this point, well, we do know, we are very confident that this is a magnetic phenomenon. Something about the magnetic field of the sun is, at this point, I put the filter back on. We know that it is tied to the magnetic field of the sun because a lot of things that are about the sun are tied to its magnetic field. The idea is that through some mechanism, this is what's not understood, you have magnetic pumping, where the magnetic field is driving the temperature. It is driving this increased speed. This is providing this larger kinetic energy to the atmosphere as a function of height. Now, how it does this? Again, it's pretty much an open question. I'm sure helio astronomers know more about it than I do, because it's, again, not my specialty. But as far as I know, while some of the details may be known, some of the observational effects may be known, the underlying mechanism is not known. What is it that's causing the magnetic field to pump gas? Can't say pump. I just can't do it. Drive the velocities up. I think it's understood how the magnetic field is interacting with the particles, but I may be wrong. But that is the consensus at this point, is that the most likely culprit here is that the sun's magnetic field is pushing through the atmosphere and causing these very, very high temperatures. And so, yeah, there you go. We're now coming out of totality, and I think the video is going to end soon, if not already. Another minute or so. But let me go back. You may have noticed something dramatic. Clive has recently reactivated Earth's closest magnetar, XT EJ 1810 minus 197. Very romantic. Incidentally, what that kind of indicates is that it has a right ascension of 18 hours, 10 minutes, and a declination of minus 19 degrees, 7 minutes. Very nice. Classy. And I think this has something to do with wanting to destroy the sun. I hope you don't actually do that, Clive. So let me go back. Oh, yeah, the video has now ended. Let me go back to something fairly dramatic. That. Okay, I'll stop playing. I'll go blind. This is a common. Oops, that's not dramatic. Shoot. There you go. Perfect. This is commonly referred to as the diamond ring. And usually you will at this point kind of have a more of a excuse me, you will have more of a pronounced ring around the in the totality. And one of the reasons why you don't is because the moon is, I think, about 2% larger than the sun. The moon is close enough in its orbit. It's not at perigee, but it's close enough to perigee that the moon is significantly larger than the sun, and so you have more of a blockage. This is known as the diamond ring, which I've cut this specifically, or at least taken images of this, like single frames. I plan on doing something with it because I love this. This is just fantastic. So now let's talk about something else about this. Let's really kind of look at this. Let's see if I can zoom in. I don't think I can with this setup. Nope, I can't. So let's first look at the moon. Look at this line as, I don't know if you can see my cursor. I think you can. Look at this line. You may notice that it's not a perfect circle. Now, if you think this is because of the camera, or this is a instrumental effect, come over here and look at this. Look at this side. This is pretty smooth. The reason why you are seeing this is because, one, it's lit up, so you can see the terrain more. But this is a good indicator of the fact that the moon is not a smooth surface. You are quite literally seeing, in this case, it's probably mountain ranges, not cratering, but it's you're seeing quote unquote mountain ranges on the moon, which are causing a change in the lunar topography as seen in this image. I love it. It's amazing. Then you have these, then let's talk about these things. This little dude, was visible friggin' naked eye. Meaning that when you looked at it, and Stephanie, I don't know if you were able to see this or not, but when it was in totality, there was a little red dot at the base of the sun. And this is oriented pretty much the same way as it would look in the sun, in the sky. It's maybe a little tilted, but yeah, there was this little red dot, and that red dot was because of this structure right here. And that structure is known as a prominence. And right now, the sun is incredibly active. It's near its solar maximum. The sun goes through cycles, not to get into the weeds of it, but because of the way that the magnetic field develops over time due to the differential rotation of the sun, the equator moves faster than the poles. Because of the way the magnetic field interacts with it, you get these sometimes very stunning displays on the surface of the sun. where the magnetic field has been kinked and is being forced up through the atmosphere, or excuse me, through the surface of the sun by convective motion underneath it. There is motion. There is rise. So there is effectively boiling in the outer layer of the sun, and that boiling it basically is pushing up this plasma, this magnetic field. It goes upwards and can actually cause the hydrogen gas in the chromosphere to condense onto the magnetic field and create these beautiful structures that you're seeing here. And again, the larger the more active the sun is, the larger the magnetic field is, or at least the more, no, I wouldn't say larger than the magnetic field, the more twisty it becomes. It becomes wibbly wobbly, not really timey wimey, but it becomes wibbly wobbly, and you get more of these events and larger events. So, but Stephanie, but were you able to see that prominence with your naked eye? Because it was real clear to us. And you can also see these other prominences. And then you have, I think, I haven't verified this, but I think one of the reasons why this was so conspicuous is that with the alignment, I believe it lined up with a crater, such that more of it was exposed. But again, I haven't verified that, but that's my intuition. But yeah. All right. So about those stars, quote unquote stars that you can see during totality. The reason is because the sun's light is effectively being blocked by the moon, you do not have nearly as much Rayleigh scattering. And so the sky brightness drops considerably. Like I said, the conditions were as if you were in twilight, either late twilight or early dusk. Which means because the sky brightness has decreased, you can see really bright objects in the night sky. I'm saying objects and quote unquote stars because the two things that you saw during totality were in fact not stars. The one that was to the right was Venus, and the one to the left was Jupiter. Now, I think there was another star that you could see during totality. I'm not sure. I'm gonna have to go back to the footage. My memory is such that there was another star that was lower down from Jupiter and obviously to the left. Again, the two prominent ones, as I said, the one to the right of the sun is actually Venus. The one to the left of the sun was actually Jupiter. If there are any other stars that were visible, I haven't actually verified what those are yet, but I can get on Stellarium and find out. How much time do I? Maybe I'll do that near the end of the stream. No, in fact, could not see Uranus. Not going to do it. Can't make me. Could not see the Devil comet because of the fact that it is too faint. Like the sky was darkened, but it was like twilight. It wasn't as if it were dead night. And the Devil comet was far too faint to be able to see. You can really only see that comet. You would only be able to see that comet if you were in a really dark sky during the totality, because one of the things that also contributed to the sky brightness is, of course, the city of Indianapolis. So, yeah, I've been told that the only way you could see it during the totality was if you were in a really, really dark environment or really, really dark location, basically very far away from everybody else. And yeah, the I'm not surprised that your security light came on. If you're in a rural environment, one of the things that was not able to experience that I've been told about is if you're in a rural environment, you know, crickets will start cricketing. Insects will start doing their nighttime insect thing. Um, Animals who feed during the night, who are nocturnal, will come out and start doing their day thing, well, night thing, and then really get freaked out when the sun comes back in like 4 minutes. Um, but because I was at the Motor Speedway, I did not, in fact, witness any of that. So yeah, let me. Speaking of the experience of it, let me move that and stop screen share. Let me see if I can find another video that was taken. This was taken by one of my students, or one of the students that was there, and it is really cool. I think it's this one. Let me make sure. Yep, this one. I'm just going to play this, and I'm just going to play this. It's 2 minutes long. I'm just going to play it without any voiceover, just so you can. It is, as I said, it is filmed by a student on, I think, his iPhone 15 Pro, and it gives you an idea of what the experience was like for everyone involved. As I said again, this was at the Motor Speedway, and so there were a considerable number of people there watching the Eclipse race. Oh, this white telescope that you see here, that's the Lund. That's a 150 or 150 millimeters. Somebody can compute, or I think that's 4 inches in imperial units, but don't quote me. Totality is starting.
Venus. Jupiter. Jonathan, this is so cool, man. All around.
So yeah, so that was. I hope you enjoyed that. That was that's what it was like sitting there with a crowd of people. You can, as you can hear, there were a number of people who were extremely enthusiastic um, about the event, and hopefully the audio came through. I don't know how well that came through, but a couple of things of note is that this is this was taken from what I have been told. This video was taken using a iPhone 15 Pro. Now, I know it was taken by an iPhone because of the formatting. It's a .mov file, so it's definitely taken by an iPhone. What the model is, as I said, it was a 15 Pro. The thing you might notice is the lighting conditions. It did not get this dark. The reason why it is so dark in this image or in this video is simply because of the auto gain or auto exposure that the camera has. The camera recognizes that you're looking at something that is fairly faint or localized as fairly faint, and so it's adjusting the gain in order to maximize your viewing experience for this object. And so it darkens everything else preferentially, or it darkens everything else as a consequence. So it did not get this dark during totality. It was much brighter. But as you can see, the Dr. Plavchan mentioned that the horizon, and let's brighten this up a bit. You can kind of see it in these images. So the actual lighting conditions were basically halfway between this and that darkness. But even here, you can see this. You have the audio was not good. Oh, all right. Darn it. But I will be posting that video. It's by itself, and I'll post it on both. I'll post it on my channel, and I'll also post it on the GMU Observatory channel. A lot of this eclipse footage and all of these eclipse videos, I'm going to post primarily there, or I'm going to post more of them there than I'm going to post on my own channel. So as to direct more traffic over to that YouTube channel. That YouTube, just so if you don't know, is GMU Observatory, and I'm hoping to be able to get that, grow that channel, and so to be perfectly honest, in order to get it monetized, because one of the things that we are finding is that our budget is not getting, because of the expanding nature of our activities here, particularly in public outreach, our budget just isn't really going as far as it used to. But anyway, you can see that you have this horizon, this what looks to be sunset along the horizon, and unfortunately, the video really doesn't show this part of it. But this glow, this orange glow, was all around. It was like seeing a sunset across the entirety of the horizon. And really, to understand that, this drives home the fact that why does it get dark? Why does it get chilly? It's because we are literally sitting in the shadow of the moon. And so effectively, what is happening here is that you are experiencing this horizon is showing you the extent of the shadow that you are sitting under. So it is very very cool. Let's see. There is at one point my voice. So one of our students, Jeremy, is the one operating the Lund. You may have heard, although apparently the audio wasn't great, you may have heard someone shout out, "Jonathan, look up." And that was me, because Jonathan was, and I'll show you what he was doing, the image that he took. He was extremely diligent with this thing. This thing was one of his favoriteest things in the observatory. He loves taking this thing out. He takes it out during the day. here on the campus so that students can have the opportunity to view the sun properly. Primarily, obviously not for the eclipse, but for sunspots and stuff. Because again, in H alpha, the sun is really cool. But during the eclipse, he was still going at it. He was still looking down at his computer. He was looking down at the images that were being taken. And I was like, dude, you're missing. I was thinking to myself, dude, you're missing it. Look up. Actually see the totality with your own eyes. So that was me. If you heard that, so yeah, that was pretty fucking awesome, I have to say. Speaking of Jonathan and his images, let's see if I can bring up a couple three. The video, the sound on the video itself isn't great, because again, while the video itself is excellent. Apparently, the mic on the camera is excellent. The mic on the other hand, apparently not as excellent. So, all right. What do I have here? Oh, I don't have them on this. I don't know why. All right, let me do this. Let's go over here, put that there. Oh, nope, that's not me. That's not. And screen. This is a Google Drive that I'm setting up for all the images and videos that we've taken. See, we have these are all mine. These are all C-star images. These are H alpha. So let's open that up. Bam. Oh wow, I got a really good one. This is what the sun looked like. That is what the sun looks like in H alpha. Very close to very close to totality. Because again, in H alpha, the problem is, and you saw that with the C-star. I had to take the filter off because the sun was too faint for me to see. In H alpha, again, it is too faint, is too filtered to actually see totality. So if you want to look at the corona, it's actually it's not the instrument that you want. But if you want to see this is badass. I love this. I mean, you can see that is the prominence that I was showing you before that could be seen naked eye. Here, you can definitively see this beautiful arc structure of that are very common with prominences. These are also prominences in the various forms of evolution of forming and such. One of them, I don't think any of these were flares, but maybe. But yeah, you can see this beautiful prominence down here. It is. I cannot stress enough how cool I think that is. Can I? No, I can't. Let's see if I can find. Here is H alpha with the sun so that earlier, or the picture I just showed was after totality. This is just prior to totality, and I love the way this is framed. In that, it's the moon is coming straight up. Now, the reason for that is because of the way the thing is mounted. With CC is an alt-az telescope, and so it actually, you see the orientation of of the sun is exactly what you would see with your eye. With the Lunt, it's on an equatorial mount, and so what you're seeing is basically the alignment in terms of uh, rise, ascension, and declination. But the more I think about this, I don't think it was properly set up. But anyway, I love the framing that Jonathan set up. Is to me is fantastic. The moon was going up and covering the sun. We have so many. So with CC is designed to take video. That's one of the options. I could take time lapse, but I was like, no, I want video. The Lunt is not set up. The camera is not really. Actually, it is set up for video. I don't know why, but Jonathan decided to take time lapse, and basically he took just image after image after image. I don't know what the exposure times are, but they're pretty small. We have a lot of images. So in order to really get that video that I want to show, we're going to have to stitch that together. And there's a lot of drift. It's not going to be easy. There's a lot of drift because, again, the mount wasn't set up strictly speaking, or it's not set up appropriately. And so there's a lot of drift with the sun because it's not tracking the sun. Let me show you. There it is. Okay. So yeah, so this is what the sun looks like in H alpha. Now remember what, although I don't think I actually showed it to you. This is what the sun looks like in H alpha. I'll come back to it. 1807. This is what the sun looks like in white light. In white light, where the light is filtered. Again, I've posted these kinds of images from CC a number of times. The reason why it's orangey is because it is blocking out a little bit more blue light than it is red. But if you really want to study the sun, H alpha is the way to go. This you can see this modeling structure. This is related to the granulation on the sun. I don't think we're actually seeing specific granules because these are too large, but I think there is, you're seeing, essentially because of the resolution of the telescope, you can see sort of large scale structure within the granulation. I am not claiming that these are what are known as supergranules, but I am fairly confident that what you're looking at is not an optical effect. But if you look over here, these dark lines, we refer to those as filaments. And effectively what these are prominences as seen from the top. So when they're on the limb, the edge of the sun, you can see them as, you're basically looking on the sides of them. Here, you're looking top down onto them. Kind of like the St. Louis Arch. If you're on the ground, you're seeing the side of it, but if you're in a helicopter or plane, you can fly over it and you would see basically as a straight line. Over here, you can see a couple of those sunspots. And then there's a spot up here, and then you have these, this brighter region is known as what we call active regions or flages. These typically precede the formation of large star spots or large star spot groups. The reason for that is because of the rising magnetic field, it actually enhances the amount of energy that is being put out from the sun at that point. But then when the magnetic field pops out and creates the spots themselves, it actually hinders the emission of light, or the passage of light out of the sun. Sunspots are not black. The only reason why they appear so is because of the limited dynamic range of the camera, the limited ability to see something really bright next to something that is considerably fainter. They aren't black. The average surface temperature of the sun is around 5,800 Kelvin, or really 5,900 Kelvin if you want to round up. The average temperature of a sunspot is around 4,000 Kelvin. So it's a considerable change in temperature. But what's happening is that because of the magnetic pressure is much larger in this localized environment, that it's stopping or impeding a good chunk of the energy that is coming from underneath, that is trying to escape out into space. It doesn't succeed in blocking all of it, obviously, because it's still 4,000 Kelvin, but it's enough that you can see the difference between the two, a sunspot and the surrounding prominences. That is an excellent question, Dr. Nimrod. How big are prominences? With the filaments, I'm not entirely certain, but what I can tell you is, let's see if I can go, see if I can actually go back. Nope. Nope. Yep. So the Earth would fit in this loop. That's how big this prominence is. And from what I would imagine, the Earth would easily fit within the loop of this prominence. This prominence is on the larger side, but that gives you a sense of scale in terms of how big these things can get. Is that they are basically the size, or bigger than the size of the Earth. They are quite remarkable. Let's see, what else do I have here? And yeah, so that's basically what we have. So there again, you can see these filaments. Sometimes they are straight lines, sometimes they are curved. Yeah, I cannot get enough of looking at these images. They are just dramatically cool, in my opinion. So yeah, I think that's all I got in terms of the Eclipse, in terms of just showing you what we have. This is one of my random totality. I just randomly took a frame. You can see that that CC is she's a small little one. I haven't measured it. I haven't looked it up, but I think the aperture is around 10 centimeters or so. And so much smaller aperture, which means the resolution is not nearly as great as the one. And so this is the same prominence. Obviously, my resolution is not good enough in order to actually see the inside of the prominence. Although this is a great example, or a great example, and the idea of angular resolution, and that just occurred to me. I can use this as a teaching tool. Is when you start getting into this, would be considered partially resolved. I can see this, that it has a certain shape, but I'm not able to discern any of the finer details inside the object. I can still very clearly see it, but I cannot determine, I cannot see very fine detail. With a larger aperture telescope, looking at the same object. The one has the angular resolution such that I can pick out that it is not just a blob of plasma, but it is in fact a loop of plasma. So, oops, that's not what I wanted. Again, these are. Oh, here you go. This is the Indy 500 Indianapolis. So, of course, they couldn't resist. Why is there no sound? Oh, because I turned it off. There you go. That is what a Indy car looks like as it's going around the track, and that's what it sounds like. What is this? Oh, this is a video. Another video that I took pre-eclipse of the sun with CC, which for some reason is not loading. Oh, there we go. And yeah, the sun doesn't really do much when it's not an eclipse. And over a course of a minute, it doesn't really rotate. So just kind of boring. What else do we have? Oh, yeah, this was me. This was filmed by one of my students, Emmy. Don't know why she decided to film it, but she did. Why didn't I take my car on the lap for a lap? They wouldn't let me for some reason. I had rented a Hyundai Santa Fe, and I thought, 2.4 liter engine or whatever it is, and yeah, this has got the power to do it. And I'm like, no, not so much. Seems to be annoying. I got asked a lot.
It's just the auto.
So yeah, that's just me being me, enjoying watching the eclipse. This is not during totality in any way. This is just me looking at the sun. Here you go. This is I also took a video of my students trying to play Reporter Rob. Put glasses on. Okay, apparently I didn't. That was not very long. Oh, how about this one? This takes forever. What is going on? All right, folks, we're 10 minutes from the eclipse. Yay! How we feeling? Woo, go GW! Yay! Woo! All right, let's go visit our telescope again and see what's going on with it. This is your news reporter, Dr. Sparks. All right, Jonathan, how's it look?
Good. We just got it center. We're gonna go ahead and hit center sun, enter, align sun, align successful. How about that?
Woo! Snazzy.
All
All right.
So let's get this camera work set up here, and we should be good to start recording. Should be a little meatball in there.
Check that out. All right. Yeah, I don't know what's going on here.
All right, last thing.
I swear I was filming.
I see that most of you are forgetting something. Hey, all right. Some of you still haven't clued in. Glasses.
So yeah. All right. Whoop, sorry. Let me do this. So yeah, that's a yes, that is what Professor Sparks does. I could have sworn I was filming like this, so I don't know why it's like that. I'm hoping that I can figure out some way to rotate it. I definitely was not filming in this like that. Anyway, so yes, yeah. So thank you for being here. Thank you for watching. That was essentially a recap of my Eclipse experience, both in terms of the images that we've been able to take, and the crowd reactions, and obviously those are the students that we took to Indy. Some of the best students in the world. Yeah, I'm very proud of them, and they mean a lot to me. So yeah, it was pretty damn awesome. Oh, before I forget, let me see if I can show you. As I said, I helped set up. Oops. Oh no, I haven't downloaded it yet. I'm still in the process of collecting all of the images and all the videos. There were some beautiful. There was actually a professional photographer at GMU because the university actually gave a shit when they realized there was 1,000 people here. So they brought out a photographer and started photographing, and we got some really, really cool shots of the crowd and images of sun through the telescopes. It was good. It was good. I like it. So yeah, again, thank you for being here. Thank you for watching. And that was my summary of my Eclipse experience. I apparently had a much better time of it than Bob did. Bob, I know, was trying to live stream, and apparently due to some computer failures and really shitty internet, he was not able to really do that. I elected not to live stream. One, because I didn't have the time, because I was doing all of this managing of these groups, didn't really have the time to sufficiently practice trying to live stream while doing recordings. And I wasn't even sure exactly how I would be able to do it. One of our tour guides figure out a way to actually share the screen of a cell phone onto a computer, which was pretty awesome. They were able to figure that out in like 15 minutes. It was pretty cool. But anyway, so I'm sure I could have figured out a way to do it, but again, I didn't really have the time. And as it got closer to the event, I was like, this is my first solar eclipse. This is the first time I'm going to see the sun in totality. I really wanted to be present in the moment. And so I didn't really want to have my attention divided between the two. And I knew I was taking videos, so I could put together, and I do plan on putting together a video, a composite video talking about the whole experience from start to finish in a more narrative sort of way. So, yes, well, guys got to take breaks, and I gotta eat some crisps, as you Brits would say. And yeah, no, I was not hiding that there were alien spacecraft orbiting the moon at that point. No, I did not. I was able to filter them. I was able to, in post, as they say, filter those out. So yeah, that's kind of one of the reasons why I didn't want to live stream, because I didn't really want to show that in real time, and I'm pretty sure that's why Bob got screwed, is because NASA was fucking with his internet access, and so yeah. Oh, sorry, Amon. That was an extremely bad faux pas. I realize you're not a Brit. You are, in fact, Irish. So, all right. So, as you Brits and Irish folks would say, crisps. Rachie gave me a little bit of a little bit of ribbing for posting that I was eating chips, because those apparently are fried potatoes or fries in your part of the world. What else? What else can I do to? What else can I say to finish this up? There were a couple other things that I wanted to mention prior, or other than the negative parallax thing. They are not. Oh, I wanted to update you on the solar project. So what I did was, and I don't know if I have it on here. I don't. Maybe I'll do a more specific update over the weekend when I've actually analyzed a lot more data. But what I've done is I had an image of the Whirlpool Galaxy, and there were quite a number of stars in the field of view of that image. And so I ignored the galaxy and just concentrated on those stars. And what I did was I determined the pixel locations of all of those stars, of about 10. Excuse me. I found the pixel locations of approximately 10 of the brightest stars in that field. I then was able, and this is something nice that CC does, is CC knows where it's looking at, and it actually plate solves, meaning that it determines the coordinates, the right ascension and declination of everything in that field. And so now I have the pixel positions, I have the right ascension and declination. I can then start computing angular distance between those stars. And I chose 10 stars because that would give me effectively nine measurement independent, or 9 measurements of angular size, or the angular distance. And because I like multiples of 3 when it comes to collecting scientific data, what that does is it gives me a number of different measures of the angular size, which I can then use to compute what is known as a plate scale. If you divide the angular distance between 2 stars by the distance between the pixels, you now know how many arc seconds is described by 1 pixel. And that is necessary because for me to do the solar experiment, because when I look at the sun, I am going to be measuring the size of the sun in pixels, but I need to convert that into an angular size. And so knowing the pixel scale is vital for that. And because I did essentially 9 times, I now have an estimate of the error in the pixel scale. And so I'm going to propagate that error forward. So at the very end, I can give you not just what the angular size of the sun is at any particular point in this experiment or in these sets of observations, but I can also tell you what the error is. How much confidence can you have in these values? Because this is an important part of science. When you are doing science, you need to include the error involved in your measurements. Thus, a person can evaluate just how confidently they can accept those values or any interpretations that the investigator might have with said values. It also occurred to me that I was, in the beginning, neglecting something. So the goal of this particular project is to determine whether or not, or how rather, well, first, whether or not it does the angular size of the sun change as a function of day, in calendar day, over the course of a year does the angular size of the sun change. But it occurred to me that because of my schedule and so forth and so on, I'm not able to look at the sun at the exact same time over the course of a year, which means that I am looking at, through different, in astronomical terms, air masses. I am looking through various lengths of the atmosphere. And because atmospheric refraction is a thing, that is going to distort, or may distort, the size of the sun. Because as has been shown by others, as the sun gets lower and lower in the sky, it actually shrinks in this dimension. I'm not sure how much it shrinks in that dimension, but pinch your head. Sorry, squirrel. So what I want to do then is one of the things that I need to do is to correct for that. One, I need to investigate it. I need to figure out, as a function of altitude, how the sun's angular size change. And the best way to do that is to spend all day doing this, is to find a place where I have a large swath of sky to deal with, and then just take regular observations of the sun at various altitudes over the course of that day. And therefore, I can then track or look at the function of the angular size, or look at the angular size as a function of air mass or altitude. And then if once I know that relationship, I can then use that relationship to correct for that with my year-long observations, such that that is no longer an issue. That is no longer a conflating variable. Again, this is in science. This is how this is done. Is that you have to identify any potential conflating variables, and you have to deal with them in one way or another. Either you have to assess whether or not specifically, you have to assess whether or not this conflating variable is going to impact your results given the precision of your instruments. And if it is, you need to figure out some way of mitigating or explaining how that variable is going to conflate your observations. And so if I can figure out what the refraction is over time, then I can, over the course of the day, I can then correct for any sort of altitude measurements. And for good measure, I plan on doing replicating this experiment probably once a month, so that if there's any change in that relationship as a function of time, I can then compensate for it. I don't anticipate that the relationship is going to change. My expectation, my hypothesis, is that the change in the size of the apparent size of the sun as a function of altitude is the same azimuthally, meaning that no matter where you're pointed along this direction, squirrel, along that direction, it's going to be the same. But that's a hypothesis, and so again, science, I need to test said hypothesis. So I need the exact time and place, maybe the same telescope height. I'm not true, but let me think about that. I don't think the telescope height is going to make a difference. The change in elevation of the places that I'm around, because sometimes I take it on the roof. A lot of my observations are taken on the observation deck on the roof, but occasionally, like today's observation, I'm going to take just prior to class today, basically at ground level. And here the elevation is, I think it's about 140 meters above sea level. But yeah, no, that's a valid question. It's a valid thing. I don't know whether or not observing height would matter. I don't think it does. But I will investigate it further. It's been a while since I've had to actually do this correction. Just slightly off topic or slightly tangent to this is one of the things that does definitely shows a function of atmospheric refraction, which I might try to do here. There's something called absolute photometry. Most of the photometry that is done at observatories, when you're looking at like light curves of, you want to know how the light changes for exoplanets, you want to know how the light changes for a binary star, anything like that. You do what is known as differential photometry. You compare the brightness of a star with respect to other stars in that same field. So you don't know what the absolute brightness is, but you do know what the brightness, how the brightness changes as a function of time. That's called differential photometry. Absolute photometry is where you are going to find what the actual apparent magnitude of a star is. That is a pain in the nuts. I've done it all of once, and it was over multiple nights because I needed because a lot of those failed. I was doing this in Emory, which is basically in Atlanta, and yeah, I barely was able to do it. It wasn't absolute photometry. There was just it sucks. The errors on my relationships were fucking miserable. Here, I don't think it's possible. I think with the sky brightness, the uneven sky brightness, I think that it would not be feasible to do it here. But I can demonstrate the relationships. And basically, in this case, what the atmosphere does is what is called extinction. Is that the star, as it goes through higher air mass or larger air mass or larger atmosphere, it will dim as the star goes down, and very much like the sun does. At sunset, you can look at the sun with an unaided eye or unfiltered eye, as opposed to when it's high up. The other thing that does, again, sunsets are a great example of it, is that it changes the color, the apparent color of the object. The object becomes redder as it goes down. So these are the things that you have to compensate for, and the way to do that is by making multiple observations of what are called standard stars that we have very good confidence in what their apparent brightnesses are in the absence of an atmosphere. So you can compare how those brightnesses change, how the color of that star changes as a function of time. So yeah, I have, in terms of the solar project, I think about 2 weeks worth of data. I haven't really had the time to investigate it, but I do have a plate scale, so I can start taking the measurements of the sun in pixels and converting them into angular sizes. Like I said, I think I have about 2 weeks worth of data spanning, I think, about a month. So I'm hoping that when I do the analysis of this, I will see something. At Indy, I did a little bit of looking at the function of the size the size as a function of altitude, but it's a small swath of the sky, so I'm not entirely certain how much of an effect I'll be able to see. So, but stay tuned. I will be doing that. Oh yeah, that was friggin' awesome. I really wish I was taking video at the time, not time lapse. Time lapse is just basically, I think it was set to 5 milliseconds. It takes an image every 5 milliseconds, and so it's choppy. Video, I would have been able to actually show you the plane flying through the field of view as I saw it through the telescope. And yeah, it was just fucking amazing. Once in a lifetime shot. I may, just for shits and giggles, send it to Astronomy Picture of the Day. Maybe they'll find it as cool as I do. Post it. That would be fantastic. That would be definitely a feather in my cap if I could actually get one of my pictures on a pod. But there we go. And I'm still trying to figure out, I know Bob just posted a video where he determined the distance to the sun based on, I think it's an Aristarchus method, where you find the angular distance between the sun and the first quarter moon, or third quarter moon, in this case first. You find that distance, and then by simple trigonometry, you can determine the distance of the sun. Which was very cool. He did it in a very precise way using a sextant. Very awesome. The only critique that I would have for it in terms of science skepticism is that he assumed the distance to the moon, and he used stellarium to determine the angular sizes of both the moon and the sun at that point. So I recognize, I'm fairly confident I know what what is going to be said by skeptics when they look at that value is, well, you assume things that are not in evidence. So I'm hoping to be able to figure out a way. I'm still working on a way to, how am I going to take this data that I'm taking and be able to show you what the distance of the sun is. So I'm getting this linear size distance ratio. That I can do. Now, getting those values absolutely, I'm trying to figure out a way to get those absolute values using the data that I have. We'll see if I'm successful. So yeah, we'll see. All right. I am Professor Parks, PhD, and I make content on astronomy, science, skepticism, and mental health. If you enjoy this content, please like, share, and subscribe, and hit that notification bell, because I'm a chaotic son of a bitch, and I do not usually go live on a regular basis. Certainly not in any particular hour during any particular day. I basically go live whenever I have the energy and I feel like it. And even then, I could get delayed. So if you want notifications, please hit those notifications if you want to watch these videos live. Thank you all for being here. Yeah, please, if you're talking about Judy, if you're talking about Bob's observation, please do post a link to this video. It's a great vid. It's short and it's very clear cut as to how he does what the method is, how he gets his data, and how he analyzes it. So yeah. Again, thank you all for watching. Thank for those of you who are watching on this on Memorex. Thank you for being here, and yeah. So love you guys. If you'd like to help, and again, e-begging segment, if you would like to help me financially, help the observatory more specifically financially, please consider becoming a patron. The funds from Patreon, all of that goes to the observatory. Memberships for the channel, though, that goes into my grubby little hands. Yeah. So if you'd like to do that, if you'd like to support me and the observatory financially, please consider those options. And with that, I'm going to go get some lunch, teach a class, take an observation of the sun, and let's see. And I really need to update this outro.